rakiet cez teleskopy až po družice. Veda je všade okolo nás. Vítajte pri ďalšej špeciálnej epizóde Vedátorského podcastu, ktorú sme nahrávali na STARMUSe a teda bude v angličtine. Táto už bude s Jozefom. Keď sme boli na festivale, tak sme dostali otázku, či by sme nechceli nahrať rozhovor so šéfkou ESI alebo so šéfkou vedy v ESE, Carole Mundell. Mal som takú malú dušičku, lebo to prišlo z ničoho nič, ale keď som si pozrel, čomu sa navenovala vo výskume, kým sa stala teda šéfkou vedy v ESA, v Európskej vesmírnej agentúre, tak tu boli podobné veci, akým sa občas aj venujem vo vede, tak som si povedal, že snad nájdeme spoločnú reč. Počas nahrávania epizódy, keď už v podstate končil festival, už začali rozkladať všetky veci okolo, tak tam bolo veľa lomozu a hluku a dvaja naši posluchači nám pomohli veľmi učesať túto epizódu, tak aby sa dala počúvať, tak snad si užijete. No už klasicky, keď tá epizóda vyjde na YouTube, treba chvíľku počkať a YouTube potom k tomu vygeneruje titulky, ktoré si viete podľa všetko aj automaticky preklopiť do slovenčiny. Nie je to úplne že 100% kvalita, ale teda ak nerozumiete po anglicky, tak treba chvíľku počkať a na YouTube sa toto všetko objaví otitulkované. Pre mňa osobne to bol veľký zážitok, dúfam, že sa ešte niekedy s Carole budeme môcť porozprávať, lebo je to že úplne že neuveriteľná kapacita a studnica vedomostí. Takže užite si epizódu Vedátorského podcastu, kde sme mali rozhovor s Carole Mundell.
We have very interesting guests here. Can you please introduce yourself for our listeners?
So my name is Professor Carole Mundell. I'm Director of Science at the European Space Agency and also Head of the European Space Astronomy Centre outside Madrid.
Good.
So we are a little busy, as you can hear right now, because we are the STARMUS festival and we are just trying to find interesting guests to, ask difficult question. My first difficult question for you is, why do we wait so long for the LISA mission?
So the LISA mission is outstanding, iconic technology that we have to invent. We had a mission called the LISA Pathfinder mission, and this was really the mission that let us test out some of our ideas. One of the things we had to do was make sure that we could fly a spacecraft that has a test mass on it. And the test mass should not know it's on a spacecraft because it has to feel gravity in the universe without actually knowing it's being flown on a spacecraft. So we actually have to develop some really pioneering technologies. For LISA,
Sounds really impossible.
it does sound impossible, doesn't it? But LISA Pathfinder showed us that it was possible. And in fact, actually, the data that we got back from LISA Pathfinder were already at the design sensitivity before the scientists did any extra calibration. So we already know we can do this. Mm-hmm. And what we have to do for the LISA mission in full is design 3 identical spacecraft, and they will each point at one another. They will make an equilateral triangle with separation of 2.5 million kilometers between each of the spacecraft. And then it will fly as a rigid triangle along an orbit behind or in front of the Earth, 1 astronomical unit away from the Sun. And so that mission, we have lots of technology to develop. We've done the studies. We think we know how to do this. And this year, our governing body, our 22 member states who pay money into ESA for the science program, agreed with us that the technology is now ready to be developed. And so we will now put our contract call out to industry. And there'll be a competition across European industry for a prime company to win to develop this mission with other companies across Europe.
So it's after RMA stage and you're moving into the manufacturer stage.
Exactly.
Oh, well, good luck with that.
Yeah, it's an iconic time. I was very excited. It was a very exciting, interesting and tense day when we actually asked our 22 member states to come to Paris and adopt not only the LISA mission, but also the Envision mission, which is our mission that will go to Venus. So adoption means that they say, yes, we approve, you should go ahead now. Design the contracts, put them out to industry and go ahead and build the mission. So 22 countries voted unanimously to support the development of both of these missions.
And what should it reveal?
Well, it will reveal the nature of space-time. I can't overstate it. We've never flown as a species an interferometer for gravitational waves in space before. It will probe a kind of space-time ripple that we're not able to do from the Earth. So at the moment we have gravitational wave detectors on the ground, and they've been iconic in helping us prove that gravitational radiation can be detected and resulted in Nobel Prizes. But it was stellar mass black holes and neutron stars that collide to produce the kind of ripples at the frequency we can detect on Earth. If we want to look at much more massive black holes, so when supermassive black holes collide, or the ripples in space-time that are the remnants of the Big Bang, we have to go to these very long baseline lengths, which means we have to go to space, which is what LISA will do.
So it's the next step from the gravitational wave conformal over.
It is. It's the next frontier, and it's the first time ever we will have probed space-time on these scales and these energies, because these are the most violent processes in the universe. What we will do is we will use galactic binaries as the calibration, the cosmic calibration for the spacecraft, to prove that we are really probing gravitational waves. And it will take us about a year to build up that knowledge, to be really testing the data that come from the mission.
And speaking of violent outbursts, you are also involved in gamma ray bursts, right?
I am. That's one of my areas of research interest. Obviously, now as Director of Science at ESA, I've put all of my research to one side because I have to be fair to all of my portfolios from the sun and outwards. But yeah, my background is in studying black holes, supermassive black holes to begin with, and then I moved into time domain astronomy and studying gamma ray bursts in real time, so real-time autonomous systems, magnetic fields, what fuels these incredible explosions, and what they can ultimately tell us about the universe.
It's interesting because I study quantum space. It is related to both black holes and gamma ray bursts. There was the detection of GRB 221.009, the most energetic one, which basically violated the current known laws of physics. And one of the possible explanations is that, space itself has some quantum structure and slows down some of the wavelengths and moves the threshold a little bit. And the other thing is, small black holes should be evaporated by Hawking radiation, but if the space has some quantum structure, then, basically it freezes the process and maybe they can be constituents of the dark matter, but before becoming the remnants, they will just evaporate very rapidly in gamma ray bursts. So it is very unfortunate we haven't seen this before. But when deciding on new assumptions, is now quantum gravity, quantum space, an achievable role in mind?
Well, I think this is one of the big unsolved frontiers of physics, obviously, to combine the laws of physics on the smallest scales governed by quantum mechanics with the laws of physics on the largest scales governed by gravity. Mm-hmm. I think one of the challenges we have, and I really push this back to our theoretical physicists, and I know you're a theoretical physicist, I'm going to put this back on your table.
I'm writing down my homework.
You have to do your homework. What you have to give us is testable predictions. So I think there are something like 24 or 26 different models of quantum gravity. None of them are complete. They all have various different constraints, and that's understandable. This is a really hard problem to solve. Some of them do produce testable predictions. So, for example, the variable speed of light, Lorentz invariance violation. And I think we have some constraints on those. I think we can go further. One of the things that I was interested in my research was actually using gamma ray bursts through cosmic distance. And if we understand the intrinsic properties of the magnetic fields, we can use a special property of the light called polarization. And actually, how does that polarization reflect potentially the quantum foam scale of the cosmos of space-time? But for me, I can design an experiment to do that, but I also need theory colleagues to come and say, here is a definitive prediction. If you measure this, then it really constrains the models. If you detect this, it constrains the models in a different way. So I think we really are at the frontiers of physics, and really progress comes step by step. So we'll have a testable prediction, we'll then go and design a mission. And in fact, we did that in my research group studying magnetic fields. So obviously gamma ray bursts, the question was, are they flows of plasma, or is that plasma actually governed by a large-scale load of magnetic fields? And it was a very clean experiment. Either the light is highly polarized, in which case you have large-scale load of magnetic fields, or it's not polarized and you just have a hydrogen flow. What was challenging was being able to get onto those gamma ray bursts in the very few minutes after the explosion, when the primordial magnetic field, if it exists, is still encoded in the light. And that was what we did in my group, where we pioneered this novel little polarimeter called Ringo, and then the successors Ringo 2 and Ringo 3, on the world's largest autonomous robotic telescope, the Liverpool telescope, just a 2-meter fully autonomous telescope. And we followed up in real-time gamma ray bursts detected by SWIFT, and we made the detection of 40% polarized light in the first minutes after the GRB. And we could also see how that polarized light evolved, and we proved that there are large-scale ordered magnetic fields. So that, for me, was a very powerful use of the scientific method. Clear distinctions between the theories. The brightness of the light and how the light changes was not a testable prediction because both models gave the same answer. You had to go look at the polarization of the light in order to distinguish the models. Mm-hmm. So I come back to quantum gravity colleagues and say, come forward with some really concrete testable predictions that we can then go and invent the technology to test.
But the tricky part is, we expect that the scale of the quantum gravity is the Planck scale, but maybe it's 4 orders below or above or something like that, and then it's difficult to make predictions. But I think there are some preliminary results with the vacuum dispersion, basically slowing down some of the wavelengths, and now mission is being built, Hermes telescope, that should be able basically to detect and then say, we need a big, maybe not even a bigger telescope, maybe faster detection rate because we need small differences, maybe larger detection area or something like this. So I think we are moving that way.
Guessing that, yeah.
And there was an interesting mission designed in Slovakia, also Czech Republic, Hungary, I think also Japan, GRB Alpha, now GRB Beta, which is a nanosatellite. Then basically one EU CubeSat, which detected gamma ray burst. Then when I think it was Fermi telescope, one of the NASA telescopes was overexposed by the data collected during the largest. Then those small satellites actually are good because they are not overexposed during the strong burst. So maybe they will also play a role, and they are very fast. And they can be built quickly, cheaply. So
deployed quickly.
Yeah, I think when you're talking about getting to the Planck scale, obviously you need to go to the highest energies if you're going to go to the second order models. I think your first order models you may do in the optical or slightly higher frequencies. I think one of the challenges is doing this across the electromagnetic spectrum, because if you just do this in the gamma rays, you're still model dependent because we still don't understand enough about the physics of the plasma flows. And I think one of the really big challenges of doing that kind of fundamental physics experiment with a source that's, millions and millions of light years away, is actually understanding the intrinsic source physics, the physics of what's going on around the black hole, in the plasma, with the magnetic fields. That's already quite complicated. And disentangling that with the propagation effects through a quantum foam across a perfect distance. But I think, we have to build up larger samples. We have to have new future missions. And my personal preference, and it's just my personal preference, if I were still in research, would be to do a polarized mission across the entire electromagnetic spectrum. Because then you can probe the synchrotron physics, the shock physics, and you can start to do that across large swathes of the sky at different cosmic distances. Maybe you can start then to get some realistic constraints on the cosmological properties of space-time. And I think in the future, when we have missions like LISA, when we have missions like New Athena, and other missions that might come from colleagues like NASA and JAXA, if we start to put that whole time domain multi-messenger world together, the role with band-based detectors with things like neutrinos, when we're starting to look at the same sources across all of those traces, hopefully we'll have enough information in the bag to disentangle the different types of physics that we'd like to probe.
So we are entering the era of multi-messenger astronomy.
For sure, yeah.
So we mentioned black holes. We didn't expect any black holes a couple of decades ago. We found the stellar black holes, supermassive black holes. Probably soon intermediate mass black hole will be announced as well. But what about microscopic black holes? Do you have any thought of it? Or is it too hypothetical and...
Well, it depends how micro. I mean, obviously, if they're really tiny, they will have evaporated already. I think it's very difficult to say.
Space might permit.
Maybe. I think it's quite challenging to say that little flash of light came from an evaporating black hole when there's so many other things that produce flashes of light. I mean, obviously, there are big ground-based facilities like the Large Synoptic Survey Telescope, the Rubin Observatory. Will start to survey the transient sky, and instead of a few hundred transients per year, we expect to see millions per night. So I think there'll be a whole tranche of data that we'll be able to mine into. I think you're right, though, in terms of the mass spectrum of black holes. We're now starting to probe so many different scales. And I know our colleagues at LIGO, Virgo, CAGRA, they keep a tally of all the different mass of black holes that we now have. So from the few solar mass black holes up to the 30 solar mass black holes that we detected with Gaia. And when you merge those together and produce ground-based detected gravitational waves, that gives you the 60 solar mass black holes and then right up to the supermassive black holes. And in fact, the Webb Space Telescope is showing us that we produce, or the universe can grow supermassive black holes very early on in the history of the universe, and we don't know how to do that. There shouldn't be enough cosmic time to grow 10 to the 9 or 10 to the 10 solar mass black hole.
If they were formed by the traditional, core collapse process, which was just some fluctuations very early in the universe, then it's still maybe explain them there.
Okay, I will take us from the theoretic approach. I will ask you, you are involved in NASA in major way. ESA, sorry. What are the three biggest missions in the nearest future you are very excited about, and can you explain a little bit?
You're restricting me to 3.
Tell us about
Well, let me tell you about the pathway that we have. So obviously last year we launched 2 iconic missions. One to go to Jupiter, which is called JUICE. And the idea of this mission, it will go and it will look to test whether the icy moons of Jupiter are actually habitable for life. We think that there are salty oceans below the icy crust, and we will actually test whether they could be habitable for life.
And one of the instruments was built in Slovakia.
Yeah.
So we are very proud.
It's a fantastic mission. There are 10 really brilliant instruments, and, across all of our member states and across, associate countries too.
Sure. Continue. I just wanted to...
Yeah, no, I'm aware of that and all the different components in there. So we're very excited about that mission. The other mission is Euclid, and this is really our dark explorer to study dark matter and dark energy in the universe and how they're coupled. So those 2 missions for me are going to really revolutionize our understanding of whole different parts of the cosmos, really, both in terms of cosmology. 95% of the universe that we don't understand, Euclid will unveil that to us. And the other extreme as whether our icy moons of Jupiter are actually habitable. And then every 2 years, up until 2037, the ESA Science Program is going to launch a major science mission. So they have all of these missions in preparation and are being prepared, ready for launch. We'll launch the SMILE mission with our Chinese colleagues, hopefully at the end of 2025, to really study the interaction between the sun and the Earth's magnetosphere. So that will be really important. We'll study that during solar maximum. We've got 2 really exciting exoplanet missions. So Plato will launch hopefully in 2026. And Orion in 29, and we'll be able to look with Plato at Earth-like planets around sun-like stars. So suddenly understanding planets like our own around other sun-like stars. Ariel will then start to look at the atmospheres of 1,000 exoplanets. So we'll actually start to look at atmospheric chemistry and the thermal properties of 1,000 planets and start to compare that with our Earth-like environment, which is kind of incredible when you think you'll be studying planetary atmospheres. It does sound like sci-fi, but it's science fact, and we're actually designing that mission and building it now across our member states. And then as we go out through 2031, 35, 37, obviously they'll have Envision, which will go to Venus, and will help us to study everything from above the top of the Venusian atmosphere right down to the core of the planet, and help us to understand why our sister planet, Venus should be like Earth, but it's so catastrophically different. Yes. It's hot, it's really hostile. We hope that Earth won't evolve to become that, but we'd like to understand more about the properties of all this.
Does the mission want to land on the Venus?
It won't land, no, but what it will do...
Because I found it in your papers that it's very difficult to land there.
There have been probes in the past that have done that, but that's not what we plan to do. What we will do, though, is we will use the oxygen-rich environment of Venus to slow our spacecraft down until it's in orbit. A thing called aerobraking, which is also technically quite hard to do. And then after that, we will launch LISA in 2035. That will take 2 years for the mission to get to its operating position in orbit around the sun. And then in 2037, we hope to launch the next big world X-ray observatory, which is called New Athena, which will study the hottest gas in the universe at 1 million degrees. So together we'll have this incredible fleet of missions that will do everything that we want to understand about our solar system, how our planets fit into the cosmic context of planets around other stars, and then ultimately right out to the nature of space-time.
All the questions will be answered.
Well, I'm sure we'll look at questions. You always open up new frontiers, but of course we're already planning the 2040s and the 2050s. So a few years ago, our scientific community came together to think about what would be the big questions we would want to be asking and answering, because obviously it takes some time to develop missions and we need to start now. So we devised...
You have to tell us the questions you are thinking.
Yeah, well, some of the big questions we want to answer really, they still are about life in the universe. And the idea is to build on... Yeah, exactly. Are we alone? That is quite existential. And we want to build on the technology that we've already developed for JUICE. And we said to our scientists over the last couple of years, if we were to go somewhere in the solar system and land and look for life, where should we go and how should we go? And there was a 2-year scientific study and a 2-year technical design study, which we published just this month. And the answer is out. We're going to Enceladus, which is one of the moons of Saturn. They've used the wonderful technology we developed for JUICE to actually do flybys of the moons of Saturn. And our scientists said, we'd like you to fly through the plume that's coming out of Enceladus, but that's not enough. We need you to land and we need you to take some samples. So we're going to devise that technology. And hopefully if our ministers come in 2025 and establish the right budgets for us, we'll have the money to start the technology development round.
Is it like landing on Europe and then drilling a hole? The plan, or...
Not Europa, no. So Europa is one of the Jupiter moons. NASA will go to Europa and go around it. It's a very hostile environment because it's very
The
close.
moon is large enough, I think, for 2 agencies.
Yeah, well, Europa is a very hostile environment, and we will fly by Europa and Io and Callisto and Ganymede, but the magnetic field properties close to Jupiter, where Europa is, are very, very hostile. So NASA's Europa Clipper is specially designed to go and study Europa. It won't land, but it will study that. We will do a flyby, and then we will study the other moons. And together, the data will be combined and give us a
So it will be flyby mission by Jupiter and landing in Saturn.
So our big 2040s mission will actually go straight to Saturn, and we'll do a flyby of some of the moons. So we've already, 20 years ago, we landed on Titan, so we know how to do that. But we'll do a flyby of the Saturn moons, the big Saturn moons, and then we will fly through the plume of Enceladus, and we will land on Enceladus, because we think Enceladus is the best target for life in the outer solar system.
Even better in Europe? Or Europe is also a good candidate, but we have to drill?
I think better, because the plume suggests that there are fissures and cracks in the surface, and that the material from potentially the ocean underneath is actually flowing out. So that's what our scientists told us. Yeah, our scientists have told they did a whole different piles of study. So there are 3 key criteria. You need an energy source, you need some liquid, and then you need to be able to access that. And so they studied all of the moons, and they put all of these different criteria together. And the one that came through that ticked all the boxes is Enceladus.
Okay. You open your door with landing on Titan. Are we returning there? At least is there a refueling mission? There's a plenty of methods.
Yeah, we're not returning to Titan because we've done that already, but NASA is hoping to return to Titan very shortly with their Dragonfly mission. So this is a development of their Martian helicopter, again, a technology demonstrator. So that'll be really nice to see what we may find on Titan. We had a soft landing on Titan because we assumed that there would be liquid methane oceans, and we thought we'd better be able to float. Turned out that it's all frozen. And so you see this incredible landing. You can see, where those rivers and oceans have flowed, and we landed on that frozen riverbed. And it's a really beautiful movie. I mean, the lander lands, you can see the dewdrop, and then you can see the sun in the distance through the hydrocarbon haze. It's absolutely stunning. To think we could do that 20 years ago just shows what we can do, we'll be able to do in the 2040s. So.
One quick ask question. What is your estimate of finding life with 10 years outside the world, obviously?
I'm very hopeful.
Very hopeful. In percent? 90%?
I can't give a percent. I'm not.
Okay.
Well, we found life on Earth. That's all I'm going to say.
Okay. Thank you very much.
Thank you very much for having time with us.
No a to už je z tohto rozhovoru všetko. Dúfam, že sa vám páčil. Ak ste doteraz počúvali a ničomu ste nerozumeli, lebo neviete po anglicky, tak prekliknite si na YouTube toto video. Mali by sa dať titulky preklopiť do slovenčiny. Všetko si tam môžete vypočuť. Ďakujeme, že nás počúvate, nájdete nás na všetkých dobrých aj horších podcastových platformách. Máme ešte nejaké vedátorské ponožky, máme novú knihu Rozhovory o vesmíre, ktorú som robil s Norby Wernerom. A čo ďalej dodať? Niekedy na jeseň plánujeme nejaké komunitné akcie a živé nahrávanie, tak sledujte Instagramový a Facebookový profil Vedátora, kde o tom budeme informovať, prípadne našu aplikáciu, kde si môžete púšťať podcasty, pridávame tam rôzne funkcie, napríklad sme pridali Dark Mode, pridali sme, alebo aspoň plánujeme pridať, rozmýšľam, kedy toto vyjde, lepšiu navigáciu v podcastoch, takže tak, aby ste mohli mať podcasty a výstupy, ktoré robíme, dostupné zadarmo, bez reklám, bez sledovania, trackovania dát a tak ďalej, je aplikácia Vedátor. No a to už je na dnes z našej strany všetko, majte sa pekne.
Veda nám ukazuje, že okolo seba vidíme len 4% vesmíru. Veda nám hovorí, ako sa zo šikovných primátov za milióny rokov stali moderní ľudia. Veda nám prináša vakcíny a lieky, uľahčuje život, naznačuje, ako bojovať s klimatickou zmenou. Ja som Tomáš Prokopčák a vedu milujem. Preto vám každý týždeň v spolupráci s našimi kolegami prinášame podcast Zoom, plný najnovších a najzaujímavejších vedeckých objavov. Zoom nájdete každú stredu na webe denníka SME alebo vo vašej podcastovej aplikácii.